Let me now give two examples of Hopf bifurcations. These two examples are highly oversimplified, but they contain the universal features that occur in any kind of Hopf bifurcation. This first example will be of a supercritical Hopf bifurcation. And this example is taken shamelessly from Strogatz's book on dynamical systems. It's the two-dimensional equation, the two-dimensional system in polar coordinates of r dot is equal to mu r minus r cubed, and theta dot is equal to omega plus b r squared. Let's ask what happens to this system as the control parameter mu is varied. Let's plot as mu is varied then the equation of motion in the r direction. So let's plot r dot as a function of r first for mu less than 0. So when mu is less than 0, r dot is negative everywhere. So the stable fixed point is at the origin, and the flow is towards the origin. If mu is equal to 0, then r dot comes into 0 with 0 slope, so this becomes a non-linearly stable fixed point. So we again have flow to the origin. It's just very slow compared to the case mu less than 0. And finally, for mu positive, now our function r dot starts off with a positive slope. And so if I look at the fixed points, there's now a stable fixed point at the origin, and a stable circular orbit at r star equals square root of mu, where theta dot star is increasing as omega plus b mu. Whereas in this range, r star was equal to 0, we see that as the control parameter changes from negative to positive, there is a continuous change in the location of the fixed point from 0 to a non-zero value of the radius.